All right, so first of all, I'd like to apologize if for some reason you wanted to come by my office today. I woke up last night, I felt terrible this morning, I still feel terrible, but I'm going to try and make it through the day. So I just came in to teach and that's it, and I'm going to go. So that's why I wasn't there, if you were trying to find me. The next thing, I passed back the test, the quizzes, sorry. And if you didn't get yours, they're up here, so you can just go ahead and come grab them. I encourage you, if you have any questions on how I graded anything, you feel like I took off too many points for something, just come by, my office, just not today, and I'll be happy to talk about that. I think I told you in the very beginning of the semester, I don't usually put the solutions to the quizzes out there because I like those to be just with me. But I'd be happy to go through any of that with you and show you the correct answers. All right? Okay, we finished up 11.1 last class, where what we were doing was we were looking at an equation that you could possibly solve the equation for z, and then you could look at z as being a function of two other variables, x and y. So we had this new idea of a function of several variables. And we talked about what the graphs of them looked like. Then we looked at the domains a little bit with the ranges, and that's pretty much what your homework was about, right? So now what we're going to do is the same thing that we did in calculus. Once you study functions, after that you start talking about limits of functions. Because evaluating a function at a specific point is pretty easy. You just plug in the x, the y, and you're done. But we're interested in knowing what's happening to functions when they start getting close to those places that they're undefined. We saw in the last class some pictures of the domains where the domains, well, the surfaces where they would kind of like dip down, they'd be like infinite, like asymptotes. And so can we recover any of that information from looking at these limits? But as we'll see, it's going to be a little bit harder than it was in two-dimensional space. All right, so remember in Cal 1, the definition of the limit, we would write lim, then x with a little arrow to a, so x approaches a, of f of x equals L. What that meant was that as x got very, very close to a, some value, that the function was approaching some constant value L. And the idea is that we approached a, but we never actually got to a. So we got like infinitely close to a. Let me see if I have a picture here. Yes, I do. All right, so here we have a function. Look at this. The function here would be f of x is sine x over x. If I say what's f of 0, you try and plug 0 in, you get 0 divided by 0. That's undefined. So we would say that this graph, this function has a hole. When you try and go to 0 and plug in, there's a hole. But from the graph of the function, you can tell that as we get closer to 0, the graph is headed up towards something, right? So what we did is I have those little dots there. Coming in from both sides, we approach 0, right? Y'all understand we're approaching 0 on the x-axis. The function's value is the height is getting closer and closer to 1, right? So we say that the limit is 1. Now, does it ever actually get to 1? No, right? It's just getting closer and closer. All right, so that's the idea from Cal 1. That's not what today is about, but it's a similar sort of approach. Okay, so here's another graph. This is what we call a piecewise function. So it's doing something, then it has a jump, and then it does something else. If I try and approach 0 from both sides, it's pretty obvious that as I get closer and closer to 0, from the left side, I'm approaching 1 again, right? But from the right side, it looks like I'm approaching, what, 0? So I get closer and closer to 0. So since the left and right-hand limits are not the same, right? Since coming in from the left and coming in from the right don't go to the same place, we would say that the limit does not exist. Do y'all remember putting like D, N, E in Cal 1? Does not exist. That's what's happening here. The limit doesn't exist. So the important thing is that in 2D, right, in a two-dimensional graph, when we talked about limits, they had to exist from both sides. To say that the limit exists means that the limit from both sides had to be going to the same place. All right, for the limit of a function of several variables, we are trying to determine where the function's headed as we get closer and closer to a point. Now, what you have to remember here is that with a function of two variables, your domain is the ground, right? And your range is actually the function, and it's like a surface, right? So when we're saying get closer and closer to something, what's the function doing? What we're getting close to is no longer a single value, like x equals 0. It's actually a point, right? We need an x and a y coordinate for that. So we call that point AB, and we write the notation for it is still lim, and now we have the ordered pair xy approaches the ordered pair AB. And then we have the function, then we say equals L. All right, understand the notation? All right, the big question is how many ways can we approach that point? So if we go back to the two-dimensional case, Cal 1, if I gave you a value x equals a, the only way you can get to this value a is if you approach it from this side or from this side, right? Two distinct directions, and that is it. Those are your only two options, two different ways. So how many ways can we approach it here? So let's look at this surface. It's a weird looking surface here. And remember, the domain is on the ground, right? And then I've transposed the domain over here so we can just kind of see it, you know, on its own. So let's say I'm trying to approach the point 0, 0. Okay? I'm trying to find the limit as we approach 0, 0 of this function. So I have this little pointer over here where I can drag around, and notice it drags it over here, and it gives us the function's value. You can't really see it. There it is. See the point right there on the surface? But we can see the value right now is what? 18.6. So let me try and drag this and get closer and closer to 0 and see what's happening. So it looks like it's approaching what? 20? It looks like 20. Now, is that the only way that I could have gone towards the origin, 0, 0? No. I could have chosen to, let's see, I could have chosen to come down the x-axis, right? Is it still approaching 20? Yeah? How about if I came down the y-axis this way? That would have worked, right? And then I could have come in this way. It looks like no matter what direction I come from, it's approaching 20, doesn't it? Now, so what do you think that means? I mean, I know in Cal 1, for the limit to exist, it had to exist from both sides, right? So what do you think it's going to mean for us to show that the limit exists? From anywhere. So what do we mean by that, though? I mean, what's anywhere? As the distance between these 2 points approaches 0, we need to be, yes, I agree. If we look at it like a disk or like a circle as we come in, right? But we can be anywhere on that circle, can't we? So let me move on and see if we can. Well, do you think that there's any function out there that when I come in this way, it's different than if I come in this way? You think that's possible? So there are infinitely many ways that we could approach. I'll show you a couple more paths. Could I have come in like this? Come in and then swing in almost like a parabola, right? That would be different than coming in a straight line, wouldn't it? Could I have come in like this? Come here. Could I have come in like a spiral motion and kind of like just, sorry, I'm not doing a very good job there, but like spiraling into 0, yes? And there's an infinite number of paths that would lead you to 0, right? I mean, there's no way you can reduce it down to 2 paths like in Cal 1, left or right. That's a huge problem for us. I mean, a significant problem. So there's infinitely many ways that we can get there. For the limit to exist, all right? For a limit to exist, the limit must exist and be the same from every path leading to that point. What's wrong with that? We can't test every path. Exactly. How in the world are you ever going to test every path? It's impossible. So what we're going to do to start out is we're going to look at some limits of some functions, and we're going to see that we're going to come in from different paths, and they're not going to be the same, which means the limit will not exist. It's going to be far easier for us to show limit does not exist than it is for us to show it does exist. Understand? So let's start with this one. We're investigating the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared, and we're going to do it along a couple of paths. So first, we're going to look at this along the x-axis. So I have a picture here. Try and make this a little bit bigger. And I think I'll make it a little darker in here, because I have a green line in there. It's kind of hard to see. And that really didn't help. Y'all want to go real dark? Will you turn off all the lights over there? That didn't help too much, did it? Okay, so let's first take a look at this surface. Kind of a strange looking surface, isn't it? Looks like some weird origami paper, right? Do y'all see it? Okay. So what I'd like for you to notice, this is the x-axis right here. All right, this is our x-axis. What I have is on the x-axis, I have a green dot, and that represents the domain. Okay, so if I'm looking at this from the top, straight down, now the black one's over the green one, but as I move, do y'all agree I'm approaching 0, 0 on the x-axis? Y'all agree? Okay, now curl that back around. This is what we've got. Okay, so this green just represents us approaching on the domain, and then the black dot is where it is on the function. Okay, so it's what's happening up on the function. So I'll bring the function back in here. And you can tell that when I'm on the x-axis, what's happening? The height is constant, right? It looks like, do I have it? Let me see if, I thought I had, oh yeah, there it is. I thought I had the function's value there. Okay, so over here. So what we can see is that as we move along the x-axis, our function is staying constant. Now, what is happening at the origin? Okay, look at this function. What is actually happening at 0, 0? At 0, 0. Not around 0, 0, at 0, 0. It's undefined, right? So this function actually has a hole in it at 0, 0. But as I approach it on the x-axis, it looks like my function just stays up at 1. We clear? Now, how are we going to show that without the graph? That's what we need to do now, all right? Show that it's 1 without this visual aid. So here's what we're going to do. We're going to take the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared. Do y'all want more light to write? Do you want a little more light? You're okay? You sure? I don't want him saying, oh, he keeps class too dark. I just want to fall asleep. All right, so here's the key though to what we're going to do now. If we are on the x-axis, right? Then what's y? If we're on the x-axis, y is 0, right? And it's fixed. We're not approaching y equals 0. We are y equals 0, right? So what I'm going to do right now is I'm going to say, if we're coming on the x-axis, that means y is exactly equal to 0. So if I rewrite this limit, notice how I changed that. I replaced my y here in the limit with 0, because y is 0, isn't it? I can't let y approach anything. It is 0. And then in the actual function, I'm going to replace y with what? 0, because it is exactly 0. And then you get x squared plus 0 squared, which is 0. And algebraically, this is just x squared over x squared, right? And whenever we have x squared over x squared, we can reduce that to become 1, can't we? Now, we can only cancel these out if we promise that x was never 0. But we are in a limit, right? And in a limit, we are saying x is getting close to 0 without actually being 0. So it's okay to make that algebraic cancellation and turn that into a 1, right? So this is just 1, and that verifies what we saw from the graph. Okay? So can we conclude now that the limit as x approaches 0, 0 of this function is 1? Can we say that? No, why not? That's only one path, right? That's only one, that we only approach the origin in one path. Remember, we have to do it for every path possible, which is going to be impossible for us to do. So this is not enough for us to say the answer is 1. What we need to do now is come in and try a different path. And what are we hoping for if we try a different path? A different answer than 1. Because if it's a different answer than 1, then we can say the limit doesn't exist. And that's what we're shooting for. On your homework problems, a lot of them will be, show this limit does not exist, which means you just have to choose paths until you get it to be two different things. Am I making sense? Okay. So now let me try, let's go on the y-axis, right? Those seem like natural choices. If I come in along the y-axis, the picture of the y-axis would look like this. So let me take the graph out of there. You can see the ground is here, right? Can y'all tell where the function is there? Yeah, it's down below it, right? You can tell right here. It says -1. But as I move along the y-axis, I'm actually down there instead of up on top. That's just because of that weird shape of this function. Now let's show it algebraically. So if we're on the y-axis, what does that say about, or what can we say then? X must be 0, right? And if x is 0, then I'm taking the limit as 0y approaches 0, 0 of what? 0 minus y squared over 0 minus, plus, sorry, y squared. And that, again, algebraically, this is just negative y squared over y squared, which is -1. Since this and this are not the same, we say the limit does not exist, right? The limit does not exist. So we come back up here, and usually don't say limit equals does not exist, you just say does not exist. DNE. That worked out okay? Make sense? All right, next. Let's investigate the limit as xy approaches 0, 0 of xy over x squared plus y squared. And we're going to do it using several paths. Here we go. I'm going to start algebraically, then I'll show you the pictures. So I'm trying for the limit as xy approaches 0, 0 of xy over x squared plus y squared. What do you want to try first? You want to do the x-axis like we did before? If we come in the x-axis, that means y is 0. What happens if you rewrite this thing with y equals 0? Limit x0 goes to 0, 0 of what? 0 over x squared. Now, when I write this, we are saying y is exactly 0, right? So this numerator isn't getting close to 0, it is 0, right? That's what we're saying? And the denominator, that is 0, so the denominator is exactly x squared. Now, I realize right now that if I let x go to 0, we're going to get 0 over 0, right? But the fact that this is 0 means that the limit is what? It's 0, right? If this number up here is exactly 0, then you don't need a limit. Does that make sense or not? So we get 0. What about if we come along the y-axis? X is equal to 0, and what would happen? Exact same thing. You're zeroing out the numerator before you can do a limit, right? You're zeroing it out. So what do we know so far? Not a whole lot, right? We know two different paths go to the same place. So maybe it is approaching 0, but I have to keep testing paths, and I have to test every single path I could ever come up with. So now I need to try something else that might not work, right? That'll give me something other than 0. Any ideas? What's another path that leads to the origin? X equals y, which is the diagonal. So far in our picture, we've come in, right, along the x-axis. We've come in along the y-axis like this, right? But why don't we draw a diagonal like this and approach through the diagonal? What is it? What's the relationship between our points if we're on this diagonal? They're the same, right? X equals y. X is equal to y, or y is equal to x. So if I come in along, we call that the identity. That means that y equals x. That means I can rewrite the limit. Instead of xy, I can write xx, approaches 0, 0. And instead of xy on top, I can put what? X squared. And on the bottom, I can put x squared plus x squared again. X squared plus x squared is 2x squared, right? So I have limit xx goes to 0, 0 of x squared over 2x squared. Now I can cancel the x squareds, can't I? Algebraically, I can cancel these. And that leaves me with what? 1/2. And I'm done. At this point, I've shown the limit doesn't exist. Coming in two different paths, it was the same, but this third path didn't work. These are the standard ones that we use, all right? When we're trying to show limits don't exist, we try the x-axis, we try the y-axis, we try the diagonal, and we hope for a change. Now the graph of this, here's the function. I'm going to pull the function out of here. Along the x-axis, it stayed 0, okay? Pull the function out of here. Along the y-axis, it stayed 0. But when we try to come in through the diagonal, everything's rotated. Let me put it this way, like that. You can see that when we come in through the diagonal, we're up above it, right? 1/2. That might be hard to see if you're looking at it from this point of view. Although maybe you could. You can kind of tell there's something crazy going on there at 0, 0, 0. Okay, how about this one? Limit xy approaches 0, 0 of xy squared over x squared plus y to the 4th. All right, let's try everything. I'm going to try and go a little quick through this. Along the x-axis, y is 0. If y is 0, can you tell me real quick what we're going to get? 0 up top, and on the bottom we'll have x squared, won't we? And that'll be 0. So I'm just going to put here that L equals 0 if we do that without showing the work. Now let's try the y-axis. If we come in the y-axis, we get x is 0. If x is 0, what do we get? 0 again. All right, then we tried the identity, right? And that was y was equal to x. If we do that, I'll write it out. We get limit xx approaches 0, 0. What will I have? X cubed over x squared plus x to the 4th. Uh-oh. What do we do here? Dun, dun, dun. Factor in x squared out on the bottom. You'll agree? So limit xx approaches 0, 0. Factor in x squared on the bottom, and then cancel. You'll have what left on top? X on the bottom. 1 plus x squared. Now let x go to 0, and what do you get? 0, right? 0 on top, 1 on the bottom. That's 0. Shit, that didn't do anything, did it? Right? So we had three strikeouts here, basically, because they're all the same. So what other path can we choose? Well, this is where things get a little weird, because we start to concede to the idea that we can't just be sitting here testing paths all day long, right? So we try and come up with a better path that covers more ground with one shot. You know, it's like you heard kill 2 birds with 1 stone type thing. Let's try and kill an infinite number of birds with 1 stone. So here's what we're going to try now. We're going to try letting y be equal to mx. Let's talk a little bit about what that would be. Y equals x was coming in through the identity, wasn't it? But if I say y equals mx, and I tell you that m can be any number, right? Then that covers all lines, all straight lines that pass through the origin, right? All straight lines going through the origin, with the exception of which one? What's that? X is so the vertical line, which was the y-axis, wasn't it? You can't get the y-axis out of that equation, can you? Because the y-axis is a vertical line. Vertical lines have undefined slopes, so you can't get it. But we've already done the y-axis, haven't we? So now that we know that we can use this, we actually don't ever have to try the x-axis, or we don't have to try the identity, because if we do this instead, it covers all of those. Well, those two. With me? All right, now I'm going to show you the picture first. And what I'm going to do is look at it from the top, and I'm going to take the surface out. So what I'm doing here is, this is y equals x, right? But I can adjust that, the m, and so if I change the m, notice that I get any of these lines, right? Now I still have to approach the origin, but I can approach it from any of those 2 lines. Okay? Y'all still with me? All right, so I'm going to go back to this view. Now look, check this out. This is kind of crazy. Remember, this is our line in our domain, and the black is the function, right? Look what's happening as we approach 0, 0. On this side, the graph dips down, then it comes back to the origin, doesn't it? On this side, it's above the green line, then dips down. So it looks like when we approach the origin from both sides on that line, our function is headed to what? 0. Now, if I rotate the line, does it change? Does it look like it changed at all? Do those black ones still look like they're doing something and then eventually go into the origin? Yeah, it looks like no matter what I use, it's going to do it. But let's actually do it algebraically. The main point of this is for you to understand that we are actually testing, with the exception of the y-axis, we're testing every single line by doing it this way. Straight line going through the origin. All right, so let's go ahead. It's going to be limit x what? mx goes to 0, 0 of, now the function was xy squared, which for us will be x mx squared, right, over x squared plus mx to the 4th, which is equal to lim, I'm just going to do this. What does the top there become? Is that m squared x to the 3rd over x squared m to the 4th x to the 4th? Should have a plus between those, shouldn't I? Now remember, m is a fixed number, right? We're not letting m go to 0 or anything like that. What we're doing is we're saying, look, if someone gives you a slope, right, any slope, m, then this is what the limit's going to turn out to be. What can we do on that? Same thing we just did a second ago, right? Factor out the x squared. If we factor out the x squared, we'll have m squared x over one plus m squared x squared, right? Now let your x go to 0. And what do you get? Pardon me? Oh, m to the 4th, thank you. We only factored an x squared out. What happens now as x goes to 0? You still get 0, don't you? You get 0 over 1, so you still get 0. I mean, that's pretty depressing, because what that means is that we tried every possible line that passes through the origin, and all those paths, as you approach 0, 0, they will eventually approach 0, 0 from both sides as you come in. Yeah? So you would really be thinking right now, yeah, this is looking pretty good that the limit is 0, but you haven't tried all paths. Right? When we say every path, we're not saying every linear path. We're saying every freaking path that you can think of. So I need something else. So try this path. The next path we're going to try is y equals x squared. I believe that's what we're going to try. Oh, no, sorry. Other way around. X equals y squared. Now, you have to first agree that that path does go to the origin. We all know what that looks like? Parabola laid sideways like this. If you move along that blue curve, does it approach the origin? Are those paths, is that path leading to the origin? Yes, right? It's nonlinear, though. So now what we're going to do is we're going to go in and rewrite the limit, replacing our x with y squared. So it becomes what? Limit as y squared y approaches 0, 0. The top is going to become y squared times y squared, because it was xy squared, wasn't it? X has been replaced with y squared, over x squared. What's x squared? It's this thing squared, so it's y to the 4th, plus y to the 4th again. Isn't this all just y to the 4th over 2y to the 4th? Which is going to give us a limit that's going to be what? 1/2. That's not 0. Therefore, this limit does not exist. So therefore, I'm going to put the limit xy squared over x squared plus y to the fourth as xy approaches 0, 0 does not exist. Yeah, but what would ever make you think to come in with that path, right? I mean, that's not a very natural choice of a path. I mean, maybe after playing with it, you kind of see how you could get things to work out in here so that they would cancel. Like, you're thinking, hey, maybe I can get everything to the fourth power, so you try that? I don't know. Here's the picture of the path that actually gave us that different result. Look at that. This is a really cool function. It's got this ridge on the top of the function, and that ridge, if you were to walk along it, is a parabola. It stays constant up here. So if I pull the graph out, you can kind of see that if I walk along that parabola, I'm up on this parabolic ridge on the surface. Stays up there at 1/2 the whole time. Make sense? Does it look like we could have done that on the other side? Yeah, it does, doesn't it? There's another ridge on the bottom. So what would we have had to have done to show it using this one? Yeah, we do x is negative y squared. Should probably work out. Good. All right, now, Squeeze Theorem. You may recall the Squeeze Theorem from Cal 1. Let me just remind you real quick. If we wanted to show the limit x approach 0 of sine x over x equals 1, that was one of the first limits that you ever learn in Cal 1. There's actually two ways to do it. You can do it with, well, there's three. There's one way you can do it that is purely geometric proof, and it's really, really nice, but it's pretty involved. And so usually I never show students the geometric proof. Then there's the Squeeze Theorem, which is what I'm going to use. And then later on in Cal 1, you learn what? L'Hopital's rule. And then if you apply L'Hopital's rule to this, it's almost instantaneous. Okay? But let's act like we don't have the L'Hopital's rule. And let's go ahead and try this. So the way the Squeeze Theorem worked was this. You have to start with a set of inequalities that you know is true. So I'm going to start here with this inequality, and everyone in here is going to agree with this, right? Everyone agrees that all sine functions are bounded between -1 and 1. That's just a statement, right? Okay, we all agreed. Then I come through here and I divide everything by x. Now, is that going to work? That's right. If x was positive, would that be okay? If x was positive? What if x was negative? What would happen? The inequalities would flip over, right? And you'd be dividing through by negative, so it would be the same thing reversed. But what happens as x goes to 0, though? Like, what happens to this as x goes to 0? That. It's what? If I plug 0, it's undefined, but what's the limit as x goes to 0 of these two? In this one, negative infinity, and right? So we get infinite limits on this side. So basically what you're be saying is that the limit in the middle would be between infinity and negative infinity, which really doesn't tell you anything, does it? So for this particular limit, this Squeeze Theorem approach would not work, because you would get negative infinity and infinity, and then this limit in here would be between those. And the squeeze theorem, for it to work, what do we need to happen? We need these two sides to go to the same thing, right? In order for us to squeeze down the one in the middle. Yeah? Okay, so I just wanted to show you that because I don't want you to misapply the squeeze theorem. I'm putting question marks out there like, okay, then if that didn't work, how could we do it? Stand by, we'll talk about it. How about this limit? How about if we change it to x goes to infinity of sine x over x? This one we can show with the squeeze theorem. Because now you may have been taught in Cal 1 just to think about this like this is a bounded function over something that becomes infinite. Anytime you have a number on top or something that's bounded and the bottom's getting bigger, it should squash down to 0, right? But if we set up the same exact inequalities that we did just a second ago, and now come through and divide by x again. Now, we definitely do not have to worry about flipping inequalities here, do we? Why? It's going to positive infinity. So that's true. And now take the limit. I'm just going to put, arrow. We're going to take the limit, limit, limit. As x goes to infinity, what's 1 over infinity go to? 0, this one, 0. And therefore, the one in the middle must also go to 0. It's squeezed between, right? So that's why this limit is 0. That's the proper application of squeeze theorem, all right? Questions? But why would we use squeeze theorem, right? Why would we use squeeze theorem? Like over here, this squeeze didn't work, so we would have to try a different one. Why not just use L'Hopital's rule? I mean, we're about to talk about squeeze theorem. Why not just do L'Hopital's rule for these new limits that we have? What do you think? What's that? What are planes? I'm talking, I guess, like this. This limit right here that we just did a second ago, right? We're trying all these different paths approaching the origin. Well, we did the same thing in Cal 1, and then later on we found out that, you could just use L'Hopital's rule, and you wouldn't have to do all that stuff. So, yeah, I mean, now we would need to talk about what would L'Hopital's rule look like here. And does L'Hopital's rule even apply when you have functions of several variables? And the answer is no. L'Hopital's rule will not apply here. It cannot apply. Now, it can, if we fix a constant, if we fix y to be something or x to be something, we're back to like a regular Cal 1 problem. But if we have both variables changing, L'Hopital's rule, it fails. So unfortunately, we're not going to ever, I'm not ever going to pull out, okay, now we can use L'Hopital. We're always going to have to use something like this. So let me give you the definition of the squeeze theorem. If you have 3 functions, each function is a function of 2 variables, and you know that the f function is squeezed and always between these two. So that's like that sine x was between -1 and 1. Now we're looking at it as these surfaces, right? Those are surfaces. It's like this one surface is always between these other 2. Now, if we take the limit of the outer 2 surfaces as we approach AB, and they squeeze to something, then the one in the middle must also go there. This is the only way we're ever going to be able to show that a limit exists for sure, is by using squeeze theorem, because you avoid having to check paths. Okay, you avoid it. So let's find the limit as x goes to 0, 0 of x squared sine squared y over x squared plus 2y squared. Using the squeeze theorem. So I'm going to take the limit as xy approaches 0, 0 of x squared sine squared y over, bless you, x squared plus 2y squared. I'd like to know what this is, and again, we're not going to, it exists, okay? The limit does exist. It is a number, but we can't check all the paths. So I'm going to start with a set of inequalities that I know is true. Do you agree with it? That's what you need to ask yourself. Do you agree with me or not? And this is the part that you would have to kind of come up with on your own, where you'd have to think about it. Do you agree with that so far? Is this quantity always bigger than or equal to 0? Yes, because everything's squared, isn't it? And I have addition down here, so we got a bunch of stuff that, you know, they would all be positive, right? At the worst, they could be zeros, which would be okay because it's equal to 0. So, yes? Okay, so that's true. Do you agree with this? Yes? Why? That's right. Look at this right here. This is the part that I'm saying this right here is smaller than that, right? Which means that if you look at the sine y squared by itself, what I'm saying to you is that the stuff in front of it, all this stuff in red, has to be smaller than 1, right? Because there's a 1 sitting in front of the sine squared y. If you believe that this red stuff is less than 1, then this is true. Now, is it less than 1? Well, x squared divided by just itself would be what? 1. But if I do x squared plus something else that's, what, positive? Or this could be 0, right? If this was 0, then this would be 1, that would be 1, and they'd be equal, wouldn't they? But if this is anything other than 0, this is a little bit bigger, so x squared plus something a little bigger is bigger than x squared. X squared divided by something bigger than it is less than 1. Yes? So, I mean, another way you could do it if you weren't convinced is you could just come over here and say, do you agree with this? Do you agree that that's less than or equal to 1? Just multiply both sides by this. Multiply it over here. Cancels, and you have x squared is less than or equal to x squared plus 2y squared. Subtract x squared on both sides, and you get this. Is that true? Yes, except when y, well, no, it's always true. When y is 0, you have equality, don't you? So what I've done now is I have trapped the thing I'm trying to figure out. Which I'm calling f of x, y. I have trapped it between two functions. But the functions are functions I actually can take the limit of. The left side, the limit is x, y approaches 0, 0 is just 0 because it's constant, right? So this side, when I take the limit, is 0. This side, I'm taking the limit as x, y approaches 0, 0. But because it's, well, why can I do this one and get an answer and not have to check every path? Why? There's no x. So we're back to Cal 1. This is just a function of one variable now. Sine squared y. Let y go to 0. Sine of 0 is 0. 0 squared is 0. So that's just going to 0. Therefore, the one in the middle must go to 0 also. And so, squeeze between. The limit is 0. I don't have to check all the paths. Questions? Therefore, the answer is 0 by the squeeze theorem. Man. All right, a couple of other definitions, and then we'll be done with this section. After you talk about the limit in Cal 1, you talk about continuity. We say continuity is the ability to basically draw a function without picking up your pencil. That's like the very loose definition of it. The technical definition was that the limit as you approached a value was equal to the function's value there, so you didn't have a hole. Same thing applies for a function of two variables. If the limit as you approach a value of the function equals the function's value there, then we say it's continuous at that point AB. The problem again is this left side, right? That limit's not easy to compute. But we have a couple of theorems that let us know which functions are continuous. So all polynomial functions are continuous on the entire domain R2. So what is a polynomial function when you have two variables? That means you've got x's and y's mixed up together with multiplication. You've got like x squared y plus y squared x. That's a polynomial in x and y. All polynomial functions of two variables are continuous everywhere. All rational functions are continuous on their implied domains. That means that they might have some holes, they might have some asymptotes, but if you look at just the domain of the function, they're nice and smooth and continuous surfaces. And then the composition of two continuous functions is also continuous on their implied domains. We won't use that a lot. It's just a result. We want to put it up here. All right, that should be the correct set of homework problems. Let me double check. I don't think the page is right, but I'll fix that too. Let's see, so 11-2. 5 through 13. It's page 632. All right. It doesn't. It's the Squeeze theorem is just using the fact that you're getting control over the function with two other functions, and you're showing that that surface always has to be between two other surfaces. And if you can show that those two other surfaces go towards a certain value without having to check paths on those two surfaces, then you're done. See, the thing is, right here, this function over here, g of xy, was the constant zero function. There, you don't have to check paths. If I tell you a function is always spitting out 0, it's always spitting out 0. There's no limit to evaluate there. So you could look at this 0 as being the xy plane, the ground, okay? Then this one right here is basically a sine function, well, a sine squared function. So it's doing this, it's like, it's hopping like this, but it's, as you approach 0, it hops in, it goes there, right? Do you follow that? But it's a function of one variable only, so you don't have to check several paths. All you have to do is check the path as y goes to 0. So this is back in a Cal 1 setting problem, but it's only because the x doesn't appear there that we don't have to worry about it. Does that make sense? You could look at it this way. Without, I don't want us to go too far off, but if this was x and this was y, hold on a second, I need this three-dimensionally. Okay, the one, I said one of them was 0, right, which was the ground. So I know that the ground was my g. The f function was bigger than or equal to that one, right? So my f was always above or equal to the ground. The other one was sine y squared. Sine y squared. So if I go, this is what sine squared y would look like if x was 0. Do you see that it's a sine squared? It looks like this. And now, since x isn't in that function, right? X, it was sine squared y. X wasn't there. That means x is free. So what this really looks like, I don't know if this kind of makes sense. Does that make sense at all? You extend these and they go the other direction too, but it's just like these sine, it's almost like cylinders that have been cut in half, and there's a bunch of them, but the x's no longer doesn't matter, right? I don't know, I hope that makes more sense, but. Yeah, okay. Yeah, that's a way of looking at it. But the fact that this h function only depended on x allowed us to find its limit without checking paths. X was basically free. Okay. All right, partial derivatives. So we were talking about L'Hopital's rule, and then, you know, if you have L'Hopital's rule, that'd be great, but what does the derivative even mean when we have a surface? All right, what does it mean? This is a big section, all right? The ideas in here are going to be with us for the rest of the class, all right? Partial derivatives. So let us begin by looking back at some Cal 1 stuff, right? If we had a function, f, we picked some value x, we found the derivative there, the derivative represented the slope of that line, right? And then we could use that to actually find the equation of that line. That's what we could do, right? You could find the slope of the line by taking the derivative, plugging in the value, and then you could actually find the equation by just using different formulas for equations of lines in two-dimensional space. So that's what we did in Cal 1. Now, the problem we encounter with functions of several variables is that we have two variables. This makes it determining a single tangent line very difficult. All right. I think this is a great picture. All right. Our axes are a little bit different. It's still the right-hand rule. Our speckled surface, right? Our x-axis is this way now. Y is this way. So we still have right-hand rule here, okay? And I have a point. Do you see that black point right there? Good thing I didn't make it a white point, huh? Black point. I'm going to move it around. Let me try and get it over here to the front of this surface. It's right here, so it's on this like front edge. Do you see it? Okay, so if I say right now, find the slope of the tangent line, it doesn't make a whole lot of sense because this is not just a curve and you have a line tangent to it anymore. You almost have to pick some direction you want to point in. Does that make sense? Like, tell me which way to point. Might be getting the carriage in front of the horse here. So let's do this. Let's fix a value of y. So let's let y be constant right now. Okay, if y is constant, and I pick some value, I don't have it here, but if I pick some constant for y, then now if I move my x, I'm no longer allowed to move in the y direction. Then I'm going to move along this green curve, aren't I? But I'm telling you right now, y is fixed. So if I'm moving along this green curve only, right, I'm only allowed to move along that green curve, then you could, if you want, come around and turn this picture like this and look at it from the side. Why is it all upside down and shit? I'm going to take the surface out of here because I think it's just getting confusing. Here's our normal view. There we go. If I look at it from the side, that looks very much like Cal 1, doesn't it? I have a curve, and I can find, it would make sense to find the slope of that line. Yes? But my y is fixed in order for me to be able to do that. Questions? Bring my surface back in here. I fixed x. Why not instead fix y? Or I'm sorry, wait, I fixed y. Now let me fix x. If I fix x, now I'm not allowed to change x, and I can move my y, I can change my y, and now I'm going to move along this curve, right? Those are two separate curves, aren't they? If I take the surface out of here and look at that from the side, again, I have a concept of a derivative and a concept of a slope of a tangent line, don't I? Now let me bring them both in here. And that's kind of hard to see. Why is that hard to see? 'Cause they're perpendicular to each other, aren't they? That's why that was hard to see. But if I looked at it from straight above, you see what this is? It's that surface cut one direction, cut the other direction. So if you were a person, okay, imagine you were a person, and your head is the top of this marker, and your feet are down here, and you're standing on the surface, you'd be like this, wouldn't you? Now, if I said fix the y value, you're on this green-black line, right? And you're facing, you'd be facing either the y-axis or away from the y-axis, wouldn't you? Or you could say you're parallel to the x-axis. And then if you're this way, you're fixing your x value, then you're now facing parallel to the y-axis. Understand? In either case, if I were standing here and I said walk that way on the surface, then the slope of the tangent line would tell you like your rate of ascent, wouldn't it? Or descent. Or if I said walk this direction, it would tell you your rate of ascent or descent in that direction. These two orthogonal directions, right? They're perpendicular. These are our classic partial derivatives. Partial meaning, in order to define partial, we have to hold one variable constant in order to talk about the derivative. Right now, it makes no sense for us to say, what's the rate of change in x, right? That's a derivative, a rate of change. What's the rate of change in x if y is also changing? So we have to hold y constant. Or we can say, what's the rate of change of y? But the only way we can do that is if we hold x constant. Now, later on, we will be able to say, instead of standing here and having to point this direction and having to point that direction, we will actually have something called the directional derivative, which will allow us to point in any direction. But for now, we're going to be stuck with just looking at these two. Now, how much of that do you think would have made sense without the picture? I've always, anytime I've tried to teach partial derivatives, even as a student of partial derivatives, I understood the basic idea. You hold a variable constant, and then you're finding the rate of change of the other. But graphically, once you see the graphical part of it, I think it's a little easier to swallow. You know, the algebra isn't, what we're going to do to get this to happen isn't that bad. But for us to see the visual part of it, you'll see how this connects later in other chapters, because I hope you'll be able to see the visual part of this. We'll see, right? Now, in order to find a partial derivative, you have to hold one constant, right? What if you hold them both constant? You can't take a derivative. It'll be zero, right? You hold both variables constant, there's no rate of change. Exactly. All right. Oh yeah, this little thing I have has different surfaces that you can do this for. You know, for here, I'll bring in our partials, take the surface out, and you can see from one direction it looks linear, right? The other direction looks somewhat parabolic. No, it was a cosine, wasn't it? It's got cosine in there. It makes sense, right? If I hold x constant, this is just a cosine curve. If I hold y constant, it's just what? A number times x, which is a line. This one, it's going to be parabolic in both directions, isn't it? One opening up, one opening down. Does that make sense? This one, parabolic, both down. All right, I hope that helps. I hope the visual part of that helps. Now, we will need to hold constant. All right, so now some notation. How do I let you know I want you to hold something constant? We have what is called our partial derivative notation. So if we're given z equals a function of x and y, if we want to hold y constant, then we call this the partial derivative with respect to x. So when we say partial derivative with respect to x, x is our variable, y is the constant. And we denote it with this notation. It's the same the way we write the function, we just put a little subscript x there. Now if we want to hold our x constant and take the derivative with respect to y, treat y like the variable, then we replace that with a y. Now you've got to get fast, quick with this. Because partial derivatives, we'll be taking them a lot. In the beginning, you can be kind of slow, but towards later on, you're going to have to really keep up to speed. All right, so we are given a function f of xy equals y cubed plus 2x plus x squared y to the fifth plus 10. Let's first find, we want to find for part A, f subscript x to 1. So I want to find the partial derivative with respect to x at the point 2, 1. That means if this is a surface, right? If this is a surface, watch, I'm going to do this. That's a surface. I'm going to walk out the x-axis 2, 1, 2. I'm going to go the y-axis 1, 1. I'm going to go up to the surface, right? I'm going to climb up on the surface, and I'm going to point which direction? The origin's right here, over here. So I went out x, out y, so I'm here. If I'm taking the partial with respect to x, which way am I pointing? Okay, maybe I should go. The origin is the corner of the room over there, okay? Like it's always been all class. X-axis is that way, y-axis is this way. If I'm going to be asking for this, I'm walking out on the x-axis how much? 2. And then out on the y-axis, 1, which puts me here. And then the surface is somewhere, right, above me or below me. I'm going to act like it's right there. I go get up on it, I climb up on it. Now I'm up on this surface, right? Which way am I pointing right now? Parallel to which axis? X-axis? Like that? So what am I holding constant? Y. So where's y? Y is this direction, right? So I'm holding this y constant. So all that stays the same. So I'm facing this way or possibly this way. Yes? That way or that way. So if I'm taking a partial with respect to x, I'm parallel to that axis. And then when I compute this, the answer, the numerical answer should be the rate of change. It's the slope as I would be going up as I went this way or down this way. An instantaneous rate of change. Again, without that picture I showed you, that would probably be comical with me doing all that. Hopefully you see that and you can see it here too in the room. All right. So to do this, I first just need to take the partial. Right? I can't plug 2, 1 in yet. If I plug 2, 1 in, I'm holding everything constant. So if I'm going to treat my y's like they're numbers, right? Just like they're numbers. What's the derivative of a number cubed? 0. It's a constant, right? Plus, what's the derivative of 2x if x is a variable here? 2. Plus, now be careful here. What's the derivative of x squared times a constant to the 5th power? It's 2 times the x times y to the 5th, and that's it, right? It's not a product rule here because this is a constant. This right here is a constant. So whenever we have a constant attached to a function, we just bring it along for the ride, don't we? So I take the 2x times that constant. plus what? 0, derivative of 10. So your partial derivative with respect to x is 2 plus 2xy to the 5th. Now let's figure out what's happening at 2, 1. Replace x with 2, y with 1, and your answer is what? 6. That's your instantaneous rate of change. If you're standing on that surface and you headed it in the direction, or you grabbed that point and you looked at the tangent line as you cut that thing, right? That curve that it would make, slope of that line is 6. Which begs the question. The question is, the slope is 6. Which side are we looking at that surface? Because if I say a slope of a line is 6, am I on this side looking at the line, or am I on this side looking at the line? Turns out it really doesn't matter to us, okay? It really doesn't matter which reference point we're going to use. Because if you're on the other side, then it's -6, and it's no big deal. Will we be able to come up with the equation of a line, you think? Sure we can. There's got to be a way, right? All right, what's the next thing we want? Fy, partial with respect to y, 2, 1. So first thing I want is the partial with respect to y. So this time I take the derivative of that, but I treat my x like a constant, right? So what's derivative of y cubed? 3y squared. What's derivative of x squared? Or 2x. That's just a constant, so it's 0. And then here it's a constant attached to y to the 5th, so it'll be x squared. Just leave it, and then derivative of y to the 5th is 5y to the 4th. So how about I put 5x squared y to the 4th? And then the derivative of 10? 0. Follow or no? All right, now let's plug in 2, 1. 2 for x, 1 for y. What are we getting there? What is it, 23? No, yeah? 23. Now the difference between that one and the one before was that I was standing here. The first one we did, I was pointed like this in this direction. The slope was 6. So if I took a step in that direction, it was sloping 6, right? If I point parallel to the y-axis, which would be this way or possibly this way, the slope is what? 23, even steeper, right? Later on, what we're actually going to be able to do is we're actually going to be able to say exactly what direction. If you were standing on the surface in a couple of sections, we're going to be able to say, hey, look, what direction do I point? So that when I take the step in that direction, it's the maximum ascent. Because I know right now if I go this way it's 6 and this way it's 23, but is there another way I could go that it would be even steeper? And what would be the steepest? And then what is the slope at the steepest? And that's going to be called the gradient. And you use that for lots of different things, all right? All right. Now, it's a partial derivative that's a little more challenging than the one we just did. So how about we take a function f of xy equals sine xy over x squared plus y squared. I think I'm going to let some light back in. So first thing we want is the partial with respect to x. I may as well show you this right now. This is, you could do that, that's okay. You don't have to write partial, you don't have to write the subscript and then xy. That's understood, just, you know, it's kind of like if you write f prime, it's understood that you meant the derivative of f. You don't have to write f prime x. These we kind of understood to be the same thing, okay? Delta, like this. Oh, del, like this. You mean like this? I've seen that notation. I've seen that notation. Actually, we're going to have the next note after this. We're going to look at all these different notations. But what's funny about it is that none of the notations I'm going to show you is this one. But it's used. Yeah. Physics probably, right? Diffie-Q, yeah. So when you see these different notations, you just have to be ready to say, oh, yeah, I know what that is. It's something I've used in the past. All right, so here's the partial. So we have to be aware of chain rule here, right? Because we have composition. We have sine, and inside sine we have, what, a quotient rule, don't we? So whenever you take the derivative of sine of something, it turns into cosine of that, right? We don't touch anything on the inside. But then chain rule says, now go inside and do your derivative in there. And that's going to be tacked onto this with multiplication. So here comes quotient rule. What is the derivative of the top of that with respect to x? Because we need it. What is it? We're trying to find the partial derivative. I'm just fucking, God, geez. It's y, right? Okay. Look, I'm trying to keep myself going here because I'm falling apart up here. Y'all can't tell, but I'm like really not feeling good. So the derivative of the top is y, correct? Because x is our variable, y is a number. So that may as well have said what, 5x up there? Derivative of 5x is 5. Derivative of yx is y. Okay, that's correct. So that's derivative of the top. Then, but quotient rule says times now the bottom minus, quotient rule now says top times derivative of the bottom, or the derivative of the bottom times the top, however you want to do it. What's the derivative of the bottom with respect to x? Just 2x, right? So 2x times now the top, which was xy. All over the whole thing, right? There we go. We won't do any more. You could clean this up. That's just the raw derivative right there, right? Bless you. And without going through all the steps, I'll just kind of write it out. The next one would be the exact same cosine out front, right? That would be the same. But now you get what? X squared plus y squared minus 2y xy over the quantity x squared plus y squared squared. So a couple of little subtle changes in there, right? X, 2y instead of y, 2x. Let it go, man. You're going to hurt yourself. Is that what it is? Is it high? Maybe that's why I feel like crap. All right. Any other questions on this? So just be careful. You know, all the rules that apply, that have applied in derivatives will apply here also. So remember what you're holding is constant. And don't confuse this with implicit differentiation. Remember where you're like, implicit differentiation where you take the derivative of y and you say it's y prime. It's not what we're doing here. Y is fixed. All right, some notation. All right, the following are equivalent. These are all different notations for partial derivatives that you may see elsewhere. Or perhaps not see elsewhere. You may see what I just showed you. This right here, call it the del f. So it's like the derivative notation, but it's this partial derivative. This stands for the partial. So the partial derivative of f, treating x as our variable. Partial derivative of z, treating our x as our variable. Now, the only reason I'm saying z is if we're saying z is f of x. All right, and then over here you could just bring the differential operator completely out and say, I'm going to take the partial derivative with respect to x of this function. Or there's even other ones. If you just write f1, d1f. This is the derivative of f with respect to the first variable. Why does the first variable mean x? The ordered pair notation, right? We had x then y, so we would have 1 would be with respect to x. Then this one kind of makes sense, right? So what if you wanted to take the partial derivative with respect to y with this notation? d2, right? And what happens if your function has 3 variables, x, y, and z? Then you can have partials there too. You can hold 2 of your variables constant and treat your third one like your variable. But that's beyond what we're doing right now. Well, hold on. No, yeah, this is, we're still talking partial derivatives. So now, just like in Cal 1, if we took the derivative, we had the idea of the second derivative and third derivative and fourth derivative. So if you want to do the second derivative, then here are some notations. This would mean right here, first take the partial derivative of f with respect to x. Then after you do that, you get an answer, right? Take the derivative of that again with respect to x. Or you could just say fxx or f11, or you could use the partial notation in here, like do the partial with respect to x of the partial of f with respect to x. Or you do this one or this one. Look at these. Look at the last two here. Have you ever, have y'all ever talked about why those are written that way? Like why the 2 in between here and on the outside here? Just for fun. I'll write it on the board. Why do that instead of that? That's right. What if I wrote this, this means take the derivative of f with respect to x, partial, and square it, right? You may think that that means this, and you may think that this means that. So what we do is we offset the exponents so that it's clear that this is a second partial, as opposed to the first partial being squared. The same thing happened in Cal 1 with derivatives. The 2's would be offset. It's not to confuse you, it's to make sure that there's no miscommunication in what you're actually computing, all right? Okay, so look, if you want to do the partial with respect to y twice, it's the same sort of thing. Here's the one that's interesting. You can do the partial with respect to x, and then whatever that answer is, take the partial of that with respect to y. But look at this notation. fxy, when you read that, you need to know which one you do first. So you read it like a book from left to right? Yes? Same thing with this one. From left to right, you read this. Oh, are these the only second partials possible? If I say you have to take derivative 2 times, partial derivative 2 times, these are the only ones possible, right? You could do with respect to x twice, with respect to y twice, with respect to x then y, or with respect to y then x. Is there any other combination? If we had a third variable, there would be more, right? But if you have a function of 2 variables, there are only 4 second partials possible. If you have a function of 3 variables, how many second partials do you have? 6? 8? What do you think would be possible? 9? You could do x, y, z, 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 because you have 3 variables now. So maybe there's a formula for it. What if you had 4 variables? How many second partials would be possible? These would be third partials, right? It's just something for you to think about. I'm sure there's some counting principle that's used there, right? If you have 2 variables, how many second partials are possible? If you have 3 variables, how many second partials are possible? How many third partial? Yeah, it'd be a counting. There's a counting principle, some factorial stuff. Yes? Could be. That'd be something that would be fun to just exercise on your own time, you know, just kind of mess with it. All right, so I don't think I'll do that one unless you want to do it. How about we find just one of the partials we haven't found so far? Like, how about we do fxy on that one? Yeah. So f of xy is x squared plus 4y to the 5th minus 10x cubed y squared. So what's fx? 2x 30y squared y squared. You agree that that's fx? Partial with respect to x? And now what's fxy? So now I do the partial of this with respect to y. This is going to go away. This just stays. 2y, 2 hits the negative 30. Negative 60, x squared y. Got it? What would fy have been? 20y to the 4th minus 20 x cubed y. I'm just doing those more so you can go back and check them. What would fyx have been? Negative 60 x squared y. Oh, they're the same. Think that's always true? The partial with respect to x then y is equal to the partial with respect to y then x. Do you think they're always the same? Not always. When they are, it's a nice thing, but they're not always. That's not always the case. All right. It does mean something. We'll see. I didn't put fxx here and fyy here. Those are missing, right? You'd still need those? Sure. I've come this far. I may as well just finish it. fxx would be 2 minus 60xy squared. And then using this one, fyy would be 80x cubed minus 20x cubed. So if you're kind of lost on those, go back and do them yourself. You should get those results. Questions? Clarets Theorem. Given z is a function of 2 variables, if f is defined on a disk that contains the point x naught, y naught, What does it mean? F is defined on a disk that contains the point F, X naught, Y naught. A disk is like a point is just a point in the domain, right? A disk is some arbitrary disk that encloses that point. That disk can have arbitrary diameter, or arbitrary radius. As long as it's defined on some arbitrarily small disk, and these two second partials are continuous, means that they are defined, they exist, then this will be true. These just give us a condition for when they're equal. Partial with respect to x first, then y is equal to y first, then x, as long as those were continuous on that disk. Not going to be a super useful thing here, just mentioning it. All right, now there's nothing that stops us from taking partials. Just like I could do first in Cal 1, first derivative, second derivative, third derivative, fourth derivative, fifth derivative, sixth. You could just keep taking derivatives, couldn't you? Well, we could do that here also. We could do, for this first one, we could find derivative with respect to x, then y again, then x. I mean, why not, right? Or we could go y, then x, then x. Now, these don't have a whole lot of meaning to us, but it can be done, right? And that would be the notation for it. Now, there are some applications of second partials that in differential equations you use, and that's what are called, this is one example of what are called Laplace equations. So when you're later on taking differential equations or some physics class, and you are trying to figure out, is there a function out there, u of xy instead of f of xy, some function, some u function of two variables that satisfies this equation? That means the second partial with respect to x and x plus the second partial with respect to y, if that's 0, then the function u is a Laplace equation, or this is a Laplace equation, but this would fall into a category of functions that satisfy Laplace equations, the Laplace equation. So, I talk about some of the applications of these equations are in mechanics, heat dynamics, fluid flow, electric potential problems. So, determine if this function is a solution to the Laplace equation. I know some people have experience with differential equations. Anyone else have some experience with differential or no? A little bit? What's the main idea behind a differential equation? I mean, the main idea is that instead of an equation like this, where you have a numeric solution, right? That's an equation. The solution to that is a number. Differential equations are equations that involve derivatives of functions. So one example of a very basic differential equation is this. What function out there is equal to its own derivative? E to the x, right? If I say y is equal to e to the x, is that a solution to that equation? Yes. E to the x is equal to the derivative of e to the x. Is that the only solution to that equation? There's the trivial solution, y is 0. The 0 function, right? What's the derivative of the 0 function? 0, so it's still equal, right? So it satisfies that differential equation. Well, later on, you try solving more complicated ones. Like, is there an equation out there that's equal to half of a derivative plus half of its second derivative? Would that work again, e to the x? E to the x, is that equal to, what's the derivative of e to the x? Itself, half of e to the x plus, what's the second derivative of e to the x? E to the x. I'm just making simple differential equations here. But you can see that they're equations that involve derivatives, and you're trying to find the y that satisfies the equation. For the Laplace thing we're doing right now, is I'm trying to see, does this function of two variables satisfy the Laplace equation? The Laplace equation is an example of a differential equation. It is this, but It uses partial derivatives. So I just need to evaluate these two things, see if you get 0. Add them together, see if you get 0. Almost out of time, but I think I can knock this out. If u is equal to x cubed plus 3xy squared, I want to see if uxx plus uyy is equal to 0. That's my question. So what's ux? 3x squared plus 3y squared. What's uxx? 6x, and that's it, right? Everyone agree? Derivative of this with respect to x is this. Derivative of that with respect to x is this. Okay, now let's do what's uy? 6x y, and then what's uyy? 6x. So is this true? What's uxx for us? 6x plus what's uyy for us? 6x. Does that equal 0? No, unless x is 0, but that's not what we're asking. We're not asking for a specific x that makes it true. We're saying, does the function itself satisfy the differential equation or not? The answer would be no here, right? So, no. It is not a solution to the Laplace equation. I'm going to have to end it. Next class, we'll finish up. All I have to do is the last example of implicit differentiation, and we'll be done with this section. The homework, I believe you can start this homework and probably get a lot of it done. Of course, the page number is not correct. It's page 639. And just so we're all on the same page, not literally like that, but next class, your take-home quiz is due, right? I said I would accept it today for extra credit if anyone had it. I'll probably have a new one for you on Wednesday. All right, a new take-home quiz. And we are how far from our test? We still got a long way to go, right? Should I take attendance? I haven't done it in a long time. Let's see who's here. Thomas is here. What the hell's today?